not around this time. And then I was feeling very bad, and then when Shiraz called, I felt I should do it. So what I'll do is basically this is a talk about it's a bit of a mixture. The second half will be about the title that I've given, but classification plus correlators of 2D rational conformal field theory. And so first let me remind you what that there's a thing called conformal bootstrap, which nowadays is very, very fashionable. It has undergone some changes in its fashionability. So it was fashionable in the 60s, it was unfashionable in the 70s and 80s. It had a brief revival in the 80s, or actually it had a revival in the 80s due to work of Belavin, Polyakov and Zamolodchikov in 2D CFT. But after 2 or 3 years of that, suddenly it kind of again started to fade out. And so I can remember that, say, in 1990, if you would talk about RCFT in a string theory place like Princeton or wherever, you would be asked, like, what's the use of this in string theory? And so it's a funny thing, because that question sometimes gets asked and sometimes is not. And nowadays, of course, nobody ever asks you what's the use of it in string theory, because most people in string theory don't actually work in string theory anymore. So it's just use of it on its own. Now, of course, there's a new use which didn't exist in 1990, which is ADS CFT. So, okay, so let me just make my points logically. Conformal bootstrap. This is a program, and to the extent so I haven't, it has many papers, spectacular works in the last few years, names like Richkov, Poland, Simmons, Duffins, etc. Sachin Jain at IISER is working on this, and I mean, there are many more names. Of course, Polyakov and also Ferrara, it turns out, are sort of some of the pioneers. Rajesh and Anindo are working on this in their group in Bangalore. So now, what is the purpose of conformal bootstrap? I think it's the classification and correlators of CFT. That's what I thought, that's what I believe it should be. So the purpose is classification of plus correlation functions of 2D CFT. So the idea is that of CFT, any kind of CFT. So the difference between this and that is simply that there I have 2D as well as R, which is rational. So generic CFT. So here the idea is you don't know where a CFT can be found. So if somebody says I'll be in dimension 3 or 4 and I'll want these operators with these dimensions, there's no guarantee that there is such a thing as a conformal field theory with all those properties. And somehow the idea is that there's some theory space, and in that there are some points, lines, some surfaces which are conformal field theories. And then there are many points, lines and parts of the space where there isn't any. So the idea is, how can we classify it? That's the conformal bootstrap program. Now the program, and what was it based on? So what should we use? So of course we use conformal invariance. We know that this imposes all kinds of constraints on the structure of correlators. For example, 2 and 3 point are determined in terms of dimensions and structure constant respectively, and then 4 point depends on one independent function in, two independent functions, the cross ratios, and higher point depend on more cross ratios. So you use that. And then of course you use something which looks very trivial, which is crossing symmetry. So for example, if you have phi x1, phi x4, then this obviously should be equal to phi x2, phi x1. So mere interchange of x1 and x2 cannot change the result. Of course, it looks very surprising that there is any content in this statement. It seems trivial. If you would calculate with a path integral, you would get a crossing symmetric answer. Otherwise, your calculation is just wrong. But you don't calculate with a path integral. You use some kind of constraints from the general structure of conformal invariance. And then that determines things up to some freedoms, and then this helps you to fix those additional freedoms. So it turns out to be a fairly non-trivial constraint. And another constraint is modular invariance. Which is the statement, well, this is a bit, so these two are in any dimension. In principle, modular invariance is also a constraint in any dimension, but now you have to have a spatial torus and then work at finite temperature, so your time is also imaginary and it's also a circle, so everything is a torus, and then you have modular invariance. I'm not sure how much has been done with modular invariance in higher dimensions, but in 2 dimensions it's particularly direct, because in 2 dimensions your space is a circle and time is the thermal circle, and there's really no loss in generality to take the space to be a circle, because that's only thing it can be. You could decompactify the circle at best, but you might as well take it to be a circle, and the time is always a Euclidean circle. So this is a 2 torus, and this is another class of constraints. Interestingly, as I'll try to mention during my talk, the mathematics of implementing this and this is not that different. Actually, it's quite similar in suitable variables in 2 dimensions.
In 2 dimensions, a space times time is conformal to R2.
A space times time is conformal to R2. Absolutely.
P2 times time in any other dimension.
That is also true. So radial quantization doesn't work. Radial quantization will, however, work if I use S2, I mean, or S3 and then a circle, but then it's not, it doesn't have obvious modular. Though I have seen some paper talking about some kind of invariance, but it becomes much more tricky. So yeah, here you have simultaneously the fact that you have S1 times S1, and that in real time this is S1 times R, which is conformal to a plane, and on the plane you can use radial quantization, and then everything becomes much easier. Okay, so these are the methods. Now, I'm not an expert on the recent developments, but as you probably know, they involve some kind of thing called semi-definite programming. Is that right? Semi-definite. Yeah, please. Yes.
So it is not a question, actually, it's a technical problem. The camera right now is zoomed out very fast. So someone needs to zoom it on the board.
Okay, okay. Thank you.
Thanks.
Right now we can't see anything.
Yeah, I see.
Okay, that's much better. Yeah. And
Okay.
maybe a little bit more. Okay, great. Yeah, a little bit out, please. Now that's too far in. Now we can, no, a little bit out, please.
Little bit out because, yeah, the whole board should come in.
Right.
Perfect, yeah. That's good.
That's good.
Okay, great. Okay.
Oh, I just draw lines with you.
Yeah, I can draw lines if you want. Okay, so here, I think from now on I'll write within this line, and here, I think here I have more freedom. Can go up to here. Okay, good.
So we need to move the lines a little bit to the right. That's perfect. Okay, yeah, good.
Okay.
You can write beyond the line, you draw the line. It's fine if you write a few inches beyond.
What did you say?
You can move a little more. You can write a
Okay,
little more.
that's fine, that's fine. It's all right, it's all right. I'll manage within this. So.
Okay.
Okay, thanks. Yeah. Yeah. So, good. So these are very general considerations, and now the question is, what do you find? And in general dimensions, you find lots of interesting things, and one of the interesting things in the last few years through semi-definite programming, which is some method of trying to implement it's something like linear programming. You try to find bounds on some functional to see if it can, some functional has to vanish, which is basically, you could call it something like a crossing functional or a modular functional, which is the difference between the left and right side of this equation, or correspondingly the modular invariance equation, which is z of 1 or minus 1 by tau in 2 dimensions at least is equal to this. So you can subtract the 2 sides of these equations, that should be 0, and then you somehow do some scan over the space of allowed things like conformal dimensions and see whether this can be 0 or not, and you find boundaries. Beyond the boundary, these kind of differences, say this minus this, will be, say, positive. If it's positive, it can't be 0. If it can't be 0, there's no conformal field theory there. So you bound the space of various parameters. The parameters typically could be conformal dimensions.
Sorry.
Yeah.
In 2 dimensions, is there a proof define all correlators?
Yeah. So actually, okay. Yeah.
So the question is, if you've got 3-point functions in
Yeah.
flat space,
Yeah.
and you've got crossing symmetry of the 4-point function,
Yes.
and modular invariance of what? Of which correlation functions?
Modular invariance, of course, is the partition function, but in principle, there's also the 1-point function on the torus. And there's something called Moore-Seiberg conditions, which I forget exactly, but I think it's basically there are some equations which follow from these, which if you satisfy, then you have a proper C. You have a well-defined. Yeah.
These conditions,
Conceptually, these are the
modular invariance
conditions.
on just the partition function is enough?
Okay, so I'm not sure if you need to additionally do the 1-point function on the torus. Now, the 2-point function on the torus can be factorized in a way to give rise to 4-point functions on the plane. So, yeah, exactly the minimal set I don't know, but I think with planar correlation functions, 4 points should be enough, certainly. And then I think these two sort of seem to, yeah.
So modular invariance of something will guarantee good correlators on arbitrary genus G sets.
It should, yes. And the logic there, the rationale there is that of course you can glue high genus surfaces. That's all 2D. Now my point was that in general D, you roam around this space of parameters and you find a model or something, and then you try to identify that model with something physical. And for example, this approach has been successful in identifying the 3D Ising model and finding its critical exponents. And just before he died, this is something very important that people in string theory should advertise. Just before he died, Kadanoff wrote a 2-page article which is on the net, just before, I mean few months before, not minutes before. And it's on the net, and it's some kind of thing titled, something roughly in praise of Richkov, Shear, Elshock, etc., or in praise of this paper. It's like a journal club article reviewing the work on 3D Ising models specifically, and saying two things. One, that these are the best bounds on the critical exponents of the 3D Ising model ever, and two, that it's more important than having good numerical values is to have a good conceptual understanding what's going on, and that in his opinion their work is the first new conceptual work in this direction. And he has compared it with a lot of other, purely numerical work in 3D Ising model obviously exists. So there are obviously some numbers to compare with. So this was a spectacular achievement. Okay, so that's for 3D. Obviously, one of the reasons string theorists care is that in 3 and 4D, this might give you CFTs which are dual to spacetimes, and they can provide a test of holography. Okay, so that's a thing. Now let's come to 2 dimensions. So in 2 dimensions, these ideas were exploited, but not using semi-definite linear programming, which seems like a bit overkill, but using something else, which is the infinite dimensional algebra. Which starts out by being a Virasoro algebra, and that too, 2 copies thereof. And this algebra gives you very powerful, it's the conformal algebra in 2 dimensions, and gives you very powerful constraints. And essentially, you can use it to implement all the things you want, but it gives you a very precise answer for, so first of all, it has a central charge, C, and in principle another one C bar for the left and right movers, but I'll assume both are equal. But when C is less than 1, then you get a series of minimal models. And there are infinitely many of these, with central charges starting at half if you're looking for unitary theories. By the way, none of this assumes unitarity, so you'll also find non-unitary theories. But supposing you want to assume unitarity, then starting from C equals half, there's an infinite series of models tending to C equals 1. And all of them exist, satisfy all the bootstrap conditions, and basically it is the realization of Polyakov's older dream of solving conformal field theories by bootstrap, but in 2 dimensions and with C less than 1. Now that's all old history. What's happened since then is that people then realized the role of extended chiral algebras.
So Sunil, about the
Yes.
existence thing, of course, many of the lower are explicitly constructed in terms of static models. But the general existence is through Zamono-Chekhov's Landau-Ginzburg description?
Okay, so when you say existence, of course, as CFTs, they certainly exist because you can calculate everything.
No, I mean construction.
So you mean, no, I guess what you mean is identification with some, by construction, what do you mean?
I mean some static model.
So StatMech model, actually the history is that there is some family called restricted solid-on-solid models, or RSOS.
Yes.
And I think Cardy was somewhere implicated in this. Cardy and Nightingale are the names which come to mind. And I think there was this, maybe Affleck, I can't remember, who actually had a one-to-one, so every unitary minimal model maps to some particular statistical model of solid-on-solid type. But the problem is those models, as statistical models, are rather abstract and mathematical, and only people like Baxter and so on really understand those. They're not the ones that real condensed matter physicists like to work with, but the first 4 or 5, as you just said, are Ising, tricritical, Ising, Potts, etc., and those are things that people know, but that's only the first 4 or 5. And then, okay, if you like a Lagrangian, then you can either use Zamono-Chekhov's Landau-Ginzburg or Dotsenko and Fathiev's Coulomb's screening charge or charge at infinity method. So there are those methods. But somehow the idea here is we should never look for a Lagrangian. We should just solve the theory and that's it. Okay. Now, the Virasoro, yeah.
Can also be obtained from positivity of Kac determinant. Is it that or
It's the same. Kac determinant allows you absolutely. So the idea is that if you want to classify consistent C less than 1 CFTs, there must necessarily be null vectors. You must necessarily decouple those. Once you decouple them, the rest of the theory is sensible and has positive definite Hilbert space. If you keep null vectors, even one of them, you have a Hilbert space which has negative norm states, and that is bad. Even the yeah, go on.
So this is not this what is crossing Bootstrap, right?
It is, well, this is a realization of Bootstrap. Okay, so the word Bootstrap comes from the fact that there's a phrase in English, picking oneself up by one's bootstraps, which is the idea that a person wearing shoes with laces can imagine picking themselves up off the ground by pulling on their laces, which clearly is a scientifically bad hypothesis, but it's used to apply to situations where you pull yourself up only with what you have, like you don't rely on external things. So the idea is that you pull yourself out of the ignorance of the field theory, but only using what you already have, which is the invariance. You don't ask for a Lagrangian or all those. Those are all crutches.
Just to say, you solve for the, you use the fact that there are null vectors to find a differential equation, which gives you conformal block.
Yeah, just about to say that. So the idea here is that for minimal models, you use null vectors, and they imply a differential equation for some holomorphic quantities from which you can construct the correlation function.
And then you're crossing to put these things together.
That's right.
And that's the bootstrap.
That's exactly that's where so the full bootstrap is that, but I think even this part of the analysis is part of bootstrap, because what data are you using? Nothing but even Kac determinant. Ultimately it comes from the Virasoro algebra, which is a consequence of conformal invariance. So the inputs are supposed to be conformal invariance and nothing else. Yeah. Now, when you come to C greater than 1, so the first thing is when C is less than 1, you can't have other algebras along with Virasoro. You only have the Virasoro algebra. Once you get to C greater than 1, then it's the other way around. Any theory with C greater than 1 has infinitely many primaries under the Virasoro algebra. So if you want to classify it using chiral algebras, there better be some other chiral algebras under which the number of primaries is finite. So the whole idea is finite number of primaries, and this is what makes the structure of these 2D CFTs so attractive. After this finite number, everything else is generated by these 2 copies of the Virasoro algebra. Okay. Now here what you can do, for example, is to have a Kac-Moody algebra, and you have finite number of primaries of that. So here, you know, the Kac-Moody algebra has generators, has currents Jn with a Lie algebra index A, and it satisfies an algebra like this. And the point is that once you have this, you can construct a Virasoro algebra in terms of this. And if something is primary of J, it's also a primary of L. But if it's a primary of L, it need not be a primary of J. In fact, J itself is a primary of L. So you use a bigger algebra to constrain your number of primaries under the whole thing. Okay. Now, what is, of course, this can go, this discussion, generic discussion can go on forever. Why am I saying this? Because in 2 dimensions, in recent years, we are in a slightly paradoxical situation. First of all, since this paper and a few of these papers, Knizhnik and Zamolodchikov famously wrote the paper on this, and Knizhnik died also soon thereafter. It was very shocking. He has 3 or 4 fabulous papers, and then at 24 or 23 he was dead, and that's the end of that. KPZ and also a couple of papers on higher genus string partition functions, and that's it. But Belavin, Knizhnik, all of those are absolute classics. You know, all are 1,000 citations plus, and we use them all the time. But anyway, after this activity ended, there was only one sort of sorry conclusion that, you know, beyond this, what lies beyond this? Are there 2D CFTs which are not any of these? Now, there are 2 divergent directions came up. One was, of course, the people who are doing this proposed the idea of coset models. So here you take a model based, a Kac-Moody theory based on a Lie algebra G, and take a coset by another Kac-Moody theory based on a Lie algebra H. And what was nice is that by manipulating G and H and the levels of G and H, you can even reproduce these minimal models, so they become special cases of that. These have no Kac-Moody algebra. So here what's happening is like a Higgs mechanism. These have some generators, these have some subset, but then no generators of this subset of this G commute with the entire subset. So all the generators are broken. It's a typical Higgs mechanism when the gauge group is completely broken, which can happen. And or you can have Higgs mechanisms where the gauge group is partially broken, and then the numerator symmetries will survive into the final theory. So these are all possible. But somehow, even today, even in papers which appear as recently on the net as last week, there's a sort of statement which suggests that 2D conformal field theories are classified by C less than 1 or C greater than 1, and in C less than 1 they are solved, and in C greater than 1 they are more complicated, but roughly they are those and these. And that's not a very satisfactory situation. So for example, something which we have known from the work of Shelikins, which is now at least 3 decades old, I think, maybe 2 decades old, 2.5 decades old, is that this is really not everything in 2D.
In 2D rational.
So, yeah, it's not everything in 2D rational conformal field theory. Now, before I return to 2D rational conformal field theory, let me talk a little bit about irrational, which is not at all a main focus of the talk, so I won't really talk much about it. Of course, there's Liouville theory, and that's not a rational conformal field theory. It doesn't fall in any minimal series. Nobody thinks it's a coset model. It has continuous families of primaries, and it's a whole harder subject, and it's well motivated in string theory. And after a lot of efforts by various people, Gervais, if people who are old enough to remember, worked for years on it. But then Kurt Wright, lots of these people, and then somehow something happened, and then the Zamolodchikovs, after a long period of dormancy, came back and wrote what is called the DOZ formula, D-O-Z-Z. But D-O are Dorn and Otto, who nobody had been paying any attention until Zamolodchikov started advertising their work. And then came Teschner, and somehow a lot of stuff happened, and that's just in the last decade or maybe 15 years or something, a lot of that. So Liouville is sort of understood, but in Liouville what you do is you somehow rely on the Lagrangian, and it's more like a vertex operator construction, a generalization of that. Now, there are other irrational CFTs. In fact, none of these Liouville nor anything I mentioned here are very popular in ADS CFT for the simple reason that you need large central charge and a sparse spectrum of primaries according to the studies from the ADS side to have a candidate CFT which is dual to ADS, and none of these is in that category. And that's part of the reason why attention hasn't been. So, the ones which are in that category are like symmetric product CFTs and so on. That's another subject. That subject doesn't use almost anything that I've written here. Of course, it will still have to use crossing symmetry and modular invariance. Now, I'm talking in 2 dimensions, but it's a different department, if you like. Department of symmetric product CFTs doesn't talk to the department of rational CFTs, which is a bit strange. And I think, I imagine that people who do Bootstrap in 2D, which are a few people, would have hoped that maybe this would somehow, you know, if you scan the modular invariance and crossing symmetry constraint using semi-indefinite programming, who's to tell you that you'll find a rational or an irrational or a, you know, symmetric product theory, the one that describes the D1, D5 system or something. You just don't know. But of course, you expect to find simpler theories first.
Rajesh has found some connection between D1, D5 and W infinity.
Yes. Right. So, there is some kind of crosstalk between these two, what I call departments, and I think maybe that's almost the only one that I know of, and I probably don't know it in enough detail. Okay, but you could take the point that, okay, let's step back a little from ADS CFT. Let's say that conformal Bootstrap is the program, and we'll be happy to learn anything we can about 2D CFT, even rational, as long as it's simple, interesting, and doesn't fall in the category of everything I've listed. If it's just one more you know, somebody might not have studied the coset of SU25 by SU23. That's not interesting because it's in principle known. One assumption, by the way, and this was mostly true, is that coset models are quite complicated because already these have many primaries, these have many primaries. The ratio has some roughly like the difference. It's not going to be that, you know, they're mostly going to be still very complicated theories for general G and H. So, there was a sense that everything in 2D RCFT reduces to this, and the surprising thing is that something different was found by Schelikens, but long ignored until Witten, as usual, brought it back, which was the following. So, observation: for a rational CFT, the partition function is the sum of mod squares of some holomorphic functions of tau summed over some number, and n, so there are n of these, and these are called characters. This is almost the definition of a rational conformal field theory. If Z can be written like this, and each of these characters starts with something, an expansion like this, 1 plus some power series in Q, then that one of them will have hi equals 0, it's the identity character, you can read off C. The others will have various h's, and these h's are guaranteed to be rational numbers if the partition function has this factorized form. It's a partially factorized form, that is, there's a mod squared and then you sum over a finite number of terms. So, this is in between having a arbitrary function, real valued function of some tau and tau bar, and having something which is just a mod squared of a complex function. That's very constrained. This is something in between that. It's not a pure mod square, but it's a sum of mod squared of terms.
So, it's only this E-type thing. I mean, the D-type
Yeah.
stuff doesn't appear.
Those can be actually rewritten. So the point is, it's not, so you might have more general things like summation I and j, mij, chi I, dagger, chi j. This is what you mean by off diagonal. But pretty often, at least in the cases I know, you can take new linear combinations of the chi I. You see, these chi I in the thing you are referring to are the characters of some particular extended chiral algebra. But you could take linear combinations of those, which are no longer the characters of that chiral algebra because they are linear combinations. But in terms of the linear combinations, you get back this form. And what I would then say is that those are the characters of the theory. So characters has two meanings in CFT. Character in Lie algebra is a well-defined meaning. Okay, but these are not necessarily characters of any Lie algebra, because we don't want rational CFT to be defined with reference to a Lie algebra. So these are just the things which have this property and give this. That's what are characters. So this kind can, as far as I know, in most or maybe all cases, be brought into that form if you just define new characters. Okay, now.
Sorry, one quick
Yes.
question.
Yes.
What was there was this paper by Moore and Seiberg which
Yes.
attempted to classify
Yeah.
which I have never read.
Hmm.
What was their conclusion?
I think the conclusion was that they classified the conditions which, if satisfied, tell you that you have a conformal field theory. But I don't think that.
They never.
I mean, it wasn't a classification. And there isn't a classification. You see, what is a classification? I guess we can all sort of agree that the analog of Lie-Dinkin classification of Lie algebras, which says that they are A, B, C, D, E, F, G series, and that's it. Of course, there are infinitely many, but this is the end of the subject. There are no more Lie algebras, simple, semi-simple, whatever Lie algebras, simple, compact, etc. So that would be a classification. Clearly, this space is, this is field theory. It's far more difficult than Lie algebra, and it's a bigger space. And what can you do? So yeah, they found some conditions. So maybe someday, if some genius classifies everything, they will have found the exhaustive solutions to those conditions, and it will include everything we've mentioned today. But since everything we mentioned today lives in really different universes, like Liouville doesn't have this form. So, it's difficult to imagine that there'll be one formalism for all this. Now, coming back to this form, the simplest RCFT will be one whose partition function is just mod of a single character squared. That's a one character theory. Now, the interesting thing is that you can actually classify one character theories, or at least you can classify some subset of them. So the reason you can is this has to be modular invariant. The only way to get a modular invariant, which is the mod squared of a holomorphic function, is for that holomorphic function to be modular invariant up to a phase. But there are strong constraints on the modular invariance of a holomorphic function. So if I tell you that this is true up to a possible phase, let's take this for simplicity the case when the phase is just not there, then it implies that chi 0 is a polynomial of j of q, where j of q is a very famous number theoretic quantity called the Klein J invariant, which has a particular expansion in Q, and which satisfies precisely this relation. The way it manages to satisfy this is that it has a pole at infinity given by this, because at infinity Q is going to 0, infinity in tau space, the torus moduli space, and there's a pole which you can see. And from this, comparing with the right side, you can see that if this was chi, then C is 24, because this is q to the minus c by 24, and this theory has no other primary fields in the sense of the character expansion. Yeah.
This was coming, you see, it can be polynomial of J.
Yes. So let's start with J. This is an example. So J is this. So if chi 0 is this, then it's C is 24. If chi 0 is a polynomial in J of degree k, then it's equal to q to the minus k plus dot dot dot, and therefore C is 24k. Now the point is that these are not minimal CFTs in any sense of, they don't belong to any of these series. We know a few sporadic things about them, but something is very weird. This J function has a constant in it, and of course a constant is modular invariant. So actually J plus any constant is also modular invariant. So the modular constraint is solved just by saying that the partition function is j plus constant, or more generally a polynomial in j which also can have a constant term, can have all kind of subleading powers also. So what constants can we add here? Well, one thing you notice is that this is one level in whatever chiral algebra there is above this state, which is clearly the ground state. So you should think of these as labeling the states of the theory. So there are 744 generators which, acting on the vacuum, give us a non-vanishing state, and these have to be spin 1 currents, because there is a theorem that if there are spin 2 chiral currents, then straight from the vacuum they come here, because L minus 1 on the vacuum is 0. If it's something of higher spin than L, it's even worse. For example, a W3 generator from here would take you straight to this term. The only thing that can take you to this term is a J, which means a Kac-Moody current. There are 744 Kac-Moody currents, and C is 24. That's a constraint to satisfy, and it's beautiful, it's very easy to satisfy. So it means that the dimension of the Kac-Moody algebra is 744, and also the central charge is 24. And there are a few solutions. One of them is E8 at level 1 crossed with itself 3 times. E8 cross E8 cross E8. So then you have, so E8 at level 1 has central charge 8. So 3 times of it has central charge 24. E8 has dimension 248, 3 times of that is 744. You're done. There's also, however, SO32 at level 1 cross E8 at level 1. Same central charge, same dimension. So that's another solution. Now the interesting thing is, in these theories, with this 744, the Kac-Moody currents of these algebras not only generate this, but after repeated application they generate a lot of other states. Obviously, that's their job. And you can sort of see that term by term. But supposing you take chi0 equals j of q minus 744. We just arbitrarily add a constant to this which removes this constant. Suddenly no Kac-Moody currents. Okay? But still all the same states at higher level. That's very weird. How can we realize a situation where there are no Kac-Moody currents and states at higher levels? Well, the only way, in fact the really only way, is that there should be 1, 9, 6, 8, 8, 4 spin 2 generators, all of which acting here take me to this level. One of them is the Virasoro generator, which is always there. So there should be 1, 9, 6, 8, 8, 3 spin 2 generators additional to the Virasoro generator. And this theory indeed has that 883 spin 2 fields. So notice that the mechanism is quite different. In this case, it was the currents of these algebras which were creating a lot of secondaries. But in this other case, there are no Kac-Moody algebras, and we still get the same number of secondaries by these spin 2 fields. And the miracle of modular invariance is that those spin 2 fields, in addition to some spin 3 fields which are independent. You see, spin 4 can be made as bilinears of spin 2. Spin 2 can be made as bilinears of spin 1, but this theory has no spin 1, so there is nothing you can do. But once you have spin 2 and 3, you can make higher chiral algebras as multilinears. So this theory has basically spin 2 and 3 chiral algebras, of which the number of spin 2 fields is this. And a famous result is that this is the dimension of the lowest irreducible representation of a discrete group called the monster group, which is the largest discrete group known. It's a sporadic group. So this is the monster CFT.
So just going back to the thing with the 744.
Yeah.
Is the statement that this is the vacuum character of the E8 to the cube?
Yes, absolutely. And now what happens is that E8 at level 1 has no primary. See, you would think there should be primaries which are those which fit inside level 1, but at level 1 the structure of E8 Lie algebra is that no primaries other than identity make it through. Same here. So therefore that's it. It just has to be that way. Okay. Now you may say, very good, now we can take any integer and add it to j of q, so we should get infinitely many 2D CFTs, but turns out this was all pure luck. Yes.
So going back to the E8 cube thing, so
Yes.
If I wrote down Wezumino-Witten model
Yeah.
level 1,
Yeah.
this thing, so
Yeah.
that theory will have only the vacuum and the stress tensor and so on and so forth.
Yes. It has the vacuum and the currents, of course. So now, for example, at level 2, it will have j minus 1 twice. So that is order of 248 squared states, and j minus 2, which is another 248. And I can't do this very quickly, but 248 squared hopefully is of this order. Am I wrong? If it's not of this order, then perhaps it also has additional spin 2 fields, but actually 60,000, not adequate. No, 240 squared, 744 squared. somebody please, quickly. 744 squared.
1000 squared is
1000 squared is much bigger than this. I think with 744 squared, we should be larger than this.
Do you want 744 squared?
553536.
You can divide by 2 and you also have to subtract all null vectors.
553536.
Very good. So much bigger than, roughly 3 times the size of this. Now, of course, divide by 2 because of some symmetry. It's order of magnitude counting. Then subtract all null vectors. As long as the number you got is bigger than this, these are the surviving states. But look at the miracle. That Kac-Moody currents produced this number of states at level 2, but there's another theory which has no Kac-Moody currents, which also has this number of states at level 2. But moreover, every level after here up to infinity is exactly the same for both the theories. It's just absolutely amazing, and it gives you a sense of the power of the conformal bootstrap.
But conformal field theories will be completely different, right? 3-point functions will be totally different.
Okay, 3-point functions are, you see the problem is they have no primaries, so 3-point functions of what? Once you go to 3-point functions of secondaries, yeah, probably they are different.
No, but even just the Cijk
of what?
Of this. Oh,
there's only the identity. Usually that's what we talk about.
Yes.
Yeah. So you, yeah.
So there are no primaries. So this could be a candidate conformal field theory dual to pure gravity, but this is C equal to 24. Sorry.
Okay, so Witten liked this theory even though it has only C equals 24 for various reasons which I really don't have time to go into, which is that this is extremal and it fits the prediction of ADS in terms of graviton and black hole state. This I cannot, if I go into that,
this is probably different.
the algebra of the currents is different. I would say that this has spin 2, spin 3 and all which are made of multilinears of the J's, while this has spin 2, spin, so this theory doesn't have monster symmetry.
Right.
That's right.
So once you start looking at the algebra, you see probably big difference.
Yeah, big differences. They are really different CFTs. But now you may think I can get infinitely many CFTs by subtracting 744 or basically adding any number larger than minus 744 up to plus infinity. I'll get j plus some other number. Now see what you have to achieve by that. Your central charge still has to be 24 and your dimension has to be whatever number. So let's consider chi naught equals, just for simple, we'll write it as this plus some new number n. So this thing has a Kac-Moody algebra of dimension n. Now you have to manufacture Kac-Moody algebras of dimension n and c equals 24, and now I invite you to try. Not easy. It's really not easy, and Schelikins did this. It was actually a wonderful piece of work which uses things like heterotic string anomaly cancellation, which had similar mathematics. And Schelikins found exactly 71 CFTs with C equals 24. They are R CFTs and they all have one character, which means Z is basically j minus 744 plus n mod squared, and n is one of 71 values, of which 0 and minus 744 are two of the values I showed you, but there are 69 more values only. So see, you satisfied modular invariance for all n, but you didn't satisfy something. There aren't theories simply. So it's clear that there's more you need than satisfying modular invariance. But this approach teaches us one thing, which is that maybe you should start by satisfying modular invariance and use modular symmetry because that's a powerful mathematical subject, and then try to narrow down by looking for theories which really exist within that space. Namely, one character theories all have this. So, this is the complete space of one character theory partition functions possible. Now, you use additional constraints to kill everything till you reach 71 theories. That's a one way of going. Yeah.
Is this the same as saying that there isn't a consistent algebra for the currents except that these values are there?
Yes, it is the same. Yes. And therefore, there can't be a theory because the currents have to be there because there are n minus 744 currents. And yes.
Can you write down the reference for that?
Schelikens? Oh gosh. Why don't you look in Inspire for Schelikens with the title Meromorphic. The reason is J has a pole at infinity of order 1, Q inverse. So, all such CFTs have, so these have basically the character has Q inverse behavior. So, that's meromorphic, simple pole at infinity. Anything else, because the conformal dimension H can be fractional, will have some more fractional behavior. The characters will have fractional behavior at infinity. So, meromorphic CFTs, that's his basic title. Okay.
So suppose
Yeah.
in addition to tau and tau bar,
Yeah.
you also turn on chemical potentials for all the kata
Yeah.
for the diagonal currents.
Yeah.
Will that not give you additional constraints or not?
I don't know actually. Chemical potentials for the car. Yeah, you could do that, of course.
But first you have to know
Yeah.
how, you would have to know how many of them commute.
Yeah, that's another thing.
Since you don't know the algebra,
Well, in the
You possibly know the rank. Okay.
Of 71 solutions of
Yeah, in those
okay,
7.
once you
Yeah.
know the-
yeah.
Like the-
Those,
Yeah.
I mean,
but those are constructions of theories,
those are constructions of theories.
so that it will work. Right? Schelikens
Yeah,
constructions
yeah,
of
yeah, yeah,
theories.
yeah. Well, by telling us what the Kac-Moody algebra is. By the way, yeah. Yeah. No, so warning. So, they are not Wess-Zumino-Witten models, because if they were, just think, one example of Schelikens theory is SU2 to the 20, SU2 to the 24. SU2 at level 1 to the 24.
That's 24 scalars, 24 free scalars.
It is 24 free scalars, each compactified on a self-dual radius circle. So, it's 24 scalars on a torus. The problem though is that the number of currents for this you can easily count. There are 3 of these. So, it's 24 times 3, 72. So, this will be the case where n is such that this whole number becomes 72. Okay, that's fine. How many primary fields does SU2 have? It has one non-trivial primary in addition to the identity, you know, the spin half primary. Raise it to the 24th power, it has of the order 2 to the 24 primaries, but this theory has no primaries. So, it's what you said earlier, it's a non-diagonal invariant of that. So, there are coincidences where a large non-simple Kac-Moody algebra has some subset of primaries which can be all collected together to add up to J. Basically, the requirement is that fish around for all things and add them up to make J. Okay. Now, with this motivation and some background which I don't probably have time to go into, 2 years ago, my master's student Harsha, who is now in Brandeis, working with Albion Lawrence and Matt Hedrick. So, we asked a very simple question: can we look for partition functions of this form, which would be analogous to the monster CFT, namely that they have no Kac-Moody algebra. Well, let me not restrict to this. We worked up to this, so either 2 or 3 terms, because that's what is practical, okay, with no Kac-Moody algebra. Now, this kind of problem had been, of course, attempted first, and the whole thing was formulated by Samir Mathur, Ashok Sen and myself in 1988 in a series of 5 papers, 88 and 89. And one thing we found was that just with 2 characters, we could find a bunch of theories which were nice Wessumino-Witten models, but which weren't related to each other as Lie algebras, but which fit into some kind of simple series of just 7 or 8 theories. Many years later, Deligne discovered those, and they are known as the Deligne series of CFTs or of Lie algebras. So I can just quickly tell you they are SU2, SU3, G2, SO8, F4, E6, E7, and E8. Normally in the study of Lie algebras, you wouldn't link all these together. But in fact, the CFTs at level 1 of all of these were exactly the outcome of our search using bootstrap ideas, using modular invariance of theories with 2 characters. This was in 88. And we were able to show that once you find them, of course, you can do 2 things. You can look at them and guess that they are Wessumino-Witten models and then use the Wessumino-Witten method to solve them. Or you can just look at them and reconstruct everything about them without having any prior knowledge about their chiral algebra. Just looking at the characters, you can reconstruct the spectrum of primaries, you can find the modular transformation among them, you can use that using Wallinder's formula to get the fusion rules, and from that you can compute correlation functions.
The
So,
levels were 1 for all of them?
the levels are 1 for all of them. Yeah, and the central charges start here at 1 and go up to 8. They are all between 1 and 8. So they are actually 1, 2, something like 14 by 5, 4, 26 by 5, 6, 7, 8. We also found this a weird theory that sits here, which many years later has been named E7.5. This is supposedly a gap in Deligne's classification. It was also a gap in our classification. There are some things that one can say about that theory. Anyway, the point is that's very interesting already, but notice that none of these has no Kac-Moody algebra. All of them have a Kac-Moody algebra, though we did also find something which also Deligne's classification contains, which is the C equals minus 22 by 5 minimal model sitting here. And that was nice because that has no Kac-Moody algebra, being a minimal model. C less than 1 minimal model, but non-unitary. But we did find it, and E7.5 actually is closely related to that one. Okay, but now the problem is, supposing we look in 3 characters, what will we find? And so the approach, I don't have time to summarize it here, is to implement modular invariance first and all other things later. And so find a set of candidate characters, partition functions, and then like Shelikins, ask if there's a theory behind that. Somewhat surprisingly, what we found with 2 or more characters is that whenever you find a modular invariant partition function, there's always a theory behind it. Unlike the 1 character case where j plus an arbitrary constant already gave infinitely many theories, 2 or more characters is more constraining, much more constraining. So 2 characters sort of was done. We redid it with some okay, so we found a new series of theories with 2 characters, but I don't have time to describe that. Then after all that, we tried to look for 3 character theories with no Kac-Moody algebra, and we found some interesting things. First of all, we found the Ising model. If we hadn't found the Ising model, we'd have been very disappointed because it's there. It's the one theory we know which has 3 characters, identity, spin field, energy operator, and it has no Kac-Moody algebra because it's a minimal model, so we found it. We found a bunch of non-unitary theories also, yes.
What do you use for this? In the last case, you said there was a polynomial.
Good, good. Thank you, thank you. I think I skipped over that way too fast. So what we use here is that if there are 3 characters and this is modular invariant, then you can always construct a differential equation with a certain covariant derivative plus some function d tau squared. So you can always construct a differential equation like this, such that the differential equation, the differential operator, it's a linear 3rd order, yeah, what?
That's out of the screen.
Oh, sorry, thank you. Okay, so it's a linear 3rd order homogeneous differential equation, and the idea is the whole equation is supposed to be modular invariant. In particular, under tau goes to -1 by tau. And for that, you can use the theory of modular forms to fix these coefficient functions up to a few small number of free parameters. These are going to be the independent solutions. So being third order, there will be 3 solutions. If the equation is invariant, the solutions don't have to be invariant. They can, under this transformation, they can permute into each other, and that's exactly what you require to make this combination modular invariant, if that permutation is really not permute but mix by a unitary matrix. So this comes from quite standard theories of Fuchsian differential equations with regular singular points and so on. In fact, this can be mapped to those. Okay, so this is the method. And what we found is it's very easy to generate such differential equations with continuous parameters. So you generate chi-i's which depend on continuous parameters. But now something else fails. You get this form, it's modular invariant, but each chi has a q expansion which is of the form q to the minus something a0 plus a1q plus a2q squared, etc. These are supposed to be numbers of states in the theory, but if they are not in positive integer, then the theory doesn't have a meaning as a CFT. So we can find this you can't do in the J function. So with a modular invariant, you automatically get, so it's if you like, it's a piece of mathematical luck that this J function has positive integer terms all the way. Supposing one of its terms, the millionth term, had a negative integer or a non-integer, it could never have described a CFT, because this is the number of states in the module above that given primary. With these differential equations, since there are parameters here, you can tune them, then a0, a1, a2 will depend on those. And we find this miracle that once in a while, this is exactly the Bootstrap ideology, once in a while for some value of the parameter, a0, a1 and a2, let's say, are all integer. So now you're excited. Now you have a candidate theory. What can you say about a3, a4, a5? Well, you can do all this using Mathematica very trivially. And you will find that once a0 up to around a6 or a7 are integer, positive, then everything up to a100, we tried 100, 1000, 5000, we just got bolder, and whatever the computer will take is always positive integer. So there's some kind of thing that once you fix the lower orders, the higher orders take care of themselves. Yes?
So this you are taking numerically or?
Not numerically in the sense of solving this differential equation by power series. It's not exactly numerical. It's just any differential equation you can solve by making an ansatz q to some power corrected by powers in q, and then just recursively solve it. So it's a recursive solution. And it's really beautiful because I've talked about it here before, because once you fix the parameters so that a few powers are positive, a few coefficients are positive integer, then so are all the coefficients. Now, when you have friends in the subject like Gabbardine, he tells you things like, well, even if you fix the first million coefficients, how do you know the million and 1th is not positive integer? So it's not a proof. But actually, he's right, but that's only because I think there's not yet a theorem about that. But for modular forms, that is single functions which are modular invariant or covariant, there is a theorem, because their spaces are finite dimensional. So if you determine some number of terms in their Q series, all the others are determined. That's why the J function has the form it has. That's why there's no CFT which can have a different partition function from the J function, because modular invariance has fixed all its coefficients to infinity. So there should be a theorem like that, and I would say that experimentally we have encountered it, but okay.
So
now, yeah.
Suppose you began with some T-type, off-diagonal modular invariant. There, your chi-i which you have eventually obtained in diagonal form, that's some kind of linear combination of what you originally had.
Yes, but it should still correspond to an integer power series. If it doesn't, I think you can, it should still correspond, because finally, you see, the final partition function is the chi-i bar. That should have, that's actually the number of states in the theory.
So you're saying, although you can't find the J raising operators this stuff, there is still some L raising, Virasoro raising operators, and the final integers would have the interpretation of being.
Well, the point is that it's a number of states. You don't care whether it was raised from somewhere by an chiral algebra or not. It is a number of states of the CFT at that level above the ground state. and every number of states should be a positive integer, or non-negative integer.
But Gautam's asking, why can't it be a positive integer in the sum, but not in individual?
Yeah, in the sum of different characters.
Yes.
Yeah, actually that's a good question. I haven't thought deeply about that. Somehow, okay, I think there's one answer to your question.
There are multiple,
No, here's an answer to your question.
Yeah.
We are not looking for the characters, those characters which would have been, of which you would be taking linear combinations. We are looking for the linear combinations. That's why we always look for diagonal things. You see, whatever the original characters, you're thinking of non-diagonal invariants because characters of a Kac-Moody algebra are a well-defined thing.
Right.
But we are not looking for a Kac, we have no prejudice about that. Okay? We are looking for the thing which, when summed like this, makes Z. So if, as you hypothetically say, there are some characters of some kind which exist such that these are linear combinations, it's these on which we are imposing the requirement of integral coefficients.
But why are you imposing them character by character, not just on this?
Because, okay, one key reason is because these all have different powers of fractional powers of Q.
So they can't cancel.
They can't cancel, yeah. It's a Q series, so, I mean, this is inside actually, but you understand. Each of these characters starts with a power of Q mod squared, and the power of Q is minus C by 24, minus C by 24 plus H1, and minus C by 24 plus H2. If H1 is H2, there is a coincidence, and then some interesting things happen. Then you get these two characters are the same, and you get a 2. Once you have this 2, you could imagine that the coefficients inside have 1 by root 2, and this 2 does the job of cancelling it. But in practice, that's not what happens. It's still integer. Okay, good. So we found the Ising model. We also found, for example, a non-unitary 2 by 7 minimal model. If you remember P and P prime, 2 and 7 makes a non-unitary theory, but it's a 3-character theory, just like the 2, 5 is a 2-character theory. Anything that was expected, we found. But we also found a new theory, at least we thought it was, with central charge 47 by 2, which this has central charge half. And notice that these pair up to make central charge 24. Okay? And what we showed, and this is of course, this turned out eventually to be a known CFT. It's called the Baby Monster CFT. And it's a 3-character theory with primary of dimension 0, the identity, 3 by 2, and 31 by 16. These are the 3 primaries. Okay, and it's a very interesting theory from number theoretic point of view also, because like the monster CFT, this one, it has 3 characters, but again the characters contain the dimensions of representations of this baby monster group. It's the second largest sporadic discrete group known. Now, one amusing thing, it looks as if I'll never get to the official topic of my talk, but I actually can summarize the result for you quite well in 5 minutes, so I'll do that at the end. Now, we encountered some other theories which we rejected, where the conformal dimension was 1, and we said, well, if there's a primary of conformal dimension 1, then it's like a current. And if it's a current, then it's not in the class of theories with no Kac-Moody algebras. And we found such a theory with central charge 8 and central charge 16, and we rejected them. And there was a very good reason, because you know that there's an E8 theory at this level and E8 cross E8 theory at this level, and they have one character. A one-character theory can always occur as solution of a third-order differential equation, because you just take the equation it satisfies and multiply by any second-order differential operator, it will still be a solution. These are like cases where the solutions of the equation don't mix under modular transformations, but just one of them is invariant. Okay. So we rejected this. Now, something strange happened last week, which I'll talk about now. I got a mail from Sangjay Lee, who was about to put a paper on the net, and that paper contained these. They had found by using semi-definite programming, all the Deligne series that I just listed, as well as this, as well as this, as well as these two, as well as a few more, on the edge of their space. So they have some space of constraints, and the edge of the space appears to realize rational conformal field theories with low numbers of characters. So this looks like a completely independent approach. Now Sheehan had already done this last year and found half of the Deligne series and not the other half. And he reported this in ISM in Pune. But when I asked him where the other half was, he said it doesn't show up, we don't know why. But these people have done something different. I think Sheehan was looking for some spectrum of conformal dimension. These people were looking for a spectrum of twists, and there's a slight difference in that. So their optimization problem was different, but on the boundary they found a bunch of interesting theories, and among them were these two. And so I wrote back saying, this is good, this is good, this is, these are spurious theories. And he said, no, no, they're not spurious. We know the conformal dimensions. So they have 3 characters and the conformal dimensions are like this. And so I looked at this some more and then realized that in fact there are such theories, and they don't have a Kac-Moody algebra because they have a 1, 1 field. They don't have a 1, 0 field. Okay? You can of course, you can take the set of characters and make the E8 theory out of it, but you don't have to. There's also a set which there's another set of combinations which is irreducible. Okay? And it's a very interesting theory because this partition function is of the form chi0 squared plus 496 chi half squared plus 33728 chi 1 squared. That's the C equals 8 theory. And the C equals 16 theory has even longer numbers appearing here. And now 2 nice things happen. First of all, now the question comes, these things were found by semi-definite programming, but how do you find that this is modular invariant? You know the characters because they arise as solutions of a 3rd order differential equation, but how do you know what is the modular transformation on them? You certainly can't read it off by knowing a few terms in the Q series. Okay. So here, this all happened last weekend. I was able to rerun the old technology and map this problem of the 3 characters of this. So we already had them, we just rejected them, but they're there in our paper. We wrongly said that they are not CFTs of the type we're looking for. I recycled some of the old technology and used it to actually compute these characters, chi 0, chi half, chi 1, exactly in terms of the lambda function. So the lambda function is, I always get it wrong, but I think this is what it is in terms of thetas. And what happens is under modular transformations, there's a, I think 2 goes to 4, 3 goes to 3, so lambda goes to 1 minus lambda.
You can do that by exactly solving the differential equation?
So you don't need to, yeah. So the point is, you can always transform the differential equation to an equation in lambda. That's quite easy, and we explain the method then. It's not obvious that it will have a solution, but something very bizarre happens in particularly the C equals 8 case, which is that the differential equation collapses to del cubed of chi hat equals 0, where chi hat is some power of lambda 1 minus lambda over 16 to the minus 2/3 into chi. So you rescale the characters you're looking for by some universal factor, and then you find that the differential equation is the simplest 3rd order differential equation in the world, namely del cubed of that is 0. The solutions are chi hat equals 1, lambda and lambda squared. You put that here. You don't get these right away, then you need to take linear combinations, but you can get these. Now one very nice thing is that for the C equals 16 case, it's much harder because the differential equation isn't so simple. So this I got yesterday from Sanjay. They solved it anyway. They were working hard on solving the equation. But there's a very simple way to determine the modular transformation of this if we know that of this, which comes from an observation we made in this paper. So these 2 theories have a very, very unusual property that to my mind still hasn't been understood, which is that the partition function, if the characters of these I call chi and the characters of this I call chi tilde, then chi 0 chi tilde 0 plus chi 1 chi tilde 1 plus chi 2 chi tilde 2. This is a kind of bilinear form. These are all holomorphic. There is no mod squared here. These are the holomorphic characters of one theory dotted with the holomorphic characters of another theory. Now notice that this goes like q to the minus 1 by 48 because of this central charge, and this goes like q to the minus 47 by 48. The total is q to the minus 1 plus dot dot dot, and we find, lo and behold, that this thing, if you evaluate it in the q series, is exactly equal to j minus 744. So this is a bilinear relation between pairs of models which both have no Kac-Moody algebra. And of course, as soon as I realized that we are looking at c equals 8 and c equals 16, you see the central charges have to add up to 24, and they do. And we immediately could prove that these, the characters of this and this, also satisfy the same bilinear relation. Okay? So you can actually solve for these in terms of those. So it's a very consistent system, and it actually makes these theories look like cosets of the monster theory. This looks like the coset of the monster theory. By that, it's very weird because cosets are always taken when you have currents, and here none of the theories under discussion has any current. So there's some generalization of the coset construction. Okay, and there's some long story about that. So now the point is, once you know all this data, you can compute the modular transformation matrix. And now you're in a very interesting position. Now the question is, you know the data, you know the characters, you're sure that they satisfy the modular invariance part. Are these conformal field theories? Now there should be correlation functions. The correlation functions should be of these non-trivial primaries like chi half and chi 1. They should have 4-point functions. How are we going to compute them? So now I'll, in the next 2 minutes, summarize the paper with Girish Muralidhara, which I had given as the title and abstract. So the thing is, if these models had been the Ising model, the answer is clear. Go to BPZ, appendix A.2 or whatever it is, and there's a null vector at level 2 above each of the spin field and the energy field. That null vector translates into a partial differential equation, then some conformalology transforms it to an ordinary differential equation, and then that differential equation you can again make into a hypergeometric or something and solve it. But how do you do that for the baby monster? It's not a minimal model. It doesn't, we don't know anything about its null vectors at all. We don't even know its chiral algebra properly because, okay, what we know is it doesn't have spin 1 currents. It was found in a search for theories without spin 1 currents. It has one Virasoro generator, big deal. It must have lots of spin 2 and spin 3 currents. What are they? We don't know. Somebody could, in this principle, this can still be done. So how do you find the correlation function? But the beautiful thing is, all you really need to do to find the correlation function is the fusion rule. And from this, you can actually find the fusion rule using this. In most of these cases, we found S to be real, so so this is Verlinde's formula, very famous one. There's in principle a dagger here, or a star, I forget which says that take this matrix, calculate this thing, and you should get positive integers. And these integers tell you, for example, that phi I tensored with phi j will give you phi k. If this is 1, this is this. If this is plus 2, then this is this with this gives you phi k twice. If this is 0, it means this tensored with this never gives you phi k. Okay. Once you have that, what you can do is to recycle the method of differential equations without any prejudice about null vectors. So use differential equations to find the correlation function g of z and z bar, where z is the cross ratio and conformal invariance says that the true correlation function g of 4 variables is some universal functions of z of these zij's times g of only z and z bar. And in a rational conformal field theory, this also is written in the form of conformal blocks summed over blocks. I should give a different index. So you see a strong parallel between the way correlation function is written and the way the partition function is written. There the variable was tau, here the variable is z. Tau and z are very different. Tau is upper half plane, z is the whole plane. But from tau you go to q, which is e to the 2 pi tau, and then to lambda, which I just showed you, and lambda is exactly like z. Not only that, lambda goes to 1 minus lambda is modular invariance, but z goes to 1 minus z is crossing. You can easily see from this that if I cross 1 with 3, then z goes to 1 minus z.
So just
Yeah.
understand. Suppose you're computing the correlation function of phi 1, phi 2, phi 3, phi 4.
Ah.
A runs over the number of indices is n1a.
Okay, if you mean all different fields?
Yes.
For different fields it's a little more complicated. So for now we focused on just the same, for the same field, yes.
So 1, 1, 1, 1.
Yes.
It's the A runs over the number of copies that you get in n11a.
Exactly, exactly, yes. Now with two characters, okay, so now you know the Ising fusion rules are actually quite simple and universal. And so the Ising fusion rules are just
Because for
yeah.
real, the 2-point functions are just delta A. There's no complex conjugate.
yeah. So if there's this in our paper we had to distinguish the case of complex fields, real fields, and so if it's complex then we would like to consider phi star, phi star, and 1 1 bar 1 1 bar. But then the entire discussion is quite different. Now what is very nice is that this information epsilon cross sigma is again sigma. This information follows from this calculation. So you didn't need to know the structure of the theory a la BPZ. You just needed to know these S's, and from that using this formula you compute this. And now what you can say is that if I'm computing, let's say, 4 phi's, then the channel in which I fuse these two, supposing all of them are sigmas, then in this channel I'll get 1 and phi epsilon and all the secondaries above both. So there are two blocks, one block where this fuses into 1 and another block where this fuses into epsilon. So we are looking for a second order differential equation as a function of z. And the two solutions will be the two blocks, and under crossing we know that the two blocks typically go into each other. Okay? So the point is that the two blocks are the block in S channel with a 1 or an epsilon exchanged. Under crossing, the two blocks are similar in the T channel with 1 and epsilon, but this goes not to one of these but to a linear combination, and this goes to another linear combination, and such that the sum of f alpha mod squared is invariant under crossing. If you see the way I phrased the problem, it's the same as exactly what we said about modular invariance. You have an invariant answer, but it comes from non-invariant holomorphic objects which transform in such a way that the answer is invariant. Okay. Now this just as we could determine the modular the equation for characters using the using modular invariance and some finite number of parameters, here we can determine the differential equation because it should be crossing symmetric, it should be second order, and we know the singularity behavior of these two when fused because we know the fusion rule, and the singularity behavior is 1 over delta sigma plus delta sigma minus delta epsilon, and we know all those. Everything was read off from the characters. It's a completely opposite way of doing the bootstrap. Once we know that, we can determine the differential equations, and once we know the differential equation, we can try to solve it. And the first thing we did, which actually is sort of known in the literature actually, and in fact Fuchs sent us a mail pointing out he had done it too many years ago. In fact, we had also done it too even many years before that, is to just try this out for the Ising model. BPZ have a concrete equation in the end of their paper, but they use a null vector we pretend we have never heard of null vectors, we get exactly the same equation and therefore the same solutions and therefore the Ising 4-point functions without ever using null vectors. So, this is a kind of different bootstrap ideology, but now you can see where I am going with this, because now consider the theory which is the Baby Monster theory with C equals 47/2. You cannot use BPZ null vector methods to find correlators of this theory. It's not a minimal model. We don't know the null vector structure. It's unitary, perfectly unitary, just not a minimal model. It's a higher spin model, if anything. If anything is known about it, it's that it must have spin 2 and spin 3 chiral algebras, but what they are exactly, I don't know. So, we don't want, and if we did know, it would be very hard to find null vectors and so on, at least I think. Maybe it's still possible, somebody should do it. But barring all that, all you have to do is notice that by the bilinear relation I showed you, the matrix S is the same in the two theories. Therefore, the fusion rules are the same in the two theories. Therefore, the differential equation is the same in the two theories, but not exactly the same because the values of conformal dimensions are not the same. I showed you that this theory has h equals 3/2 and h equals 31/16, not the Ising values. In fact, 2 minus the Ising values, which is part of this story. So, you plug in these new values into the differential equation and hey presto, you have the correlation function of the Baby Monster theory, and now you can crank this and do this to find correlation functions of all kinds of CFTs which are rational, which have small number of primaries, but which are not of the chiral algebra classification type, in fact which are much simpler than most of those and which are sporadic sort of. So, that is the content of this paper with Girish, was to write down the most general 4-point differential equations as long as they were only second order. A lot of complications come in if you have higher order. These are theories which are complicated, but their differential equations are of low order. Just like the monster theory is complicated, but it has just one character. So, it is a different type of complication. It is not the complication of an SU25 Kac-Moody theory, which is complicated only because its rank is large, but it's intrinsically the structure is governed completely by Kac-Moody symmetry. So, I also hope that this will be some way forward to unravel a little more the role of higher spin fields in CFT, which have been used, but I don't think that much new has been learnt about them as such, like where they appear and, for example, I don't know that people talk about them, maybe people talk about their minimal series, they do actually, and there are null vectors, but these don't seem to be minimal in that sense. They're non-minimal in some sense. So, that's interesting. So, that's all I want to say. Sorry, it's gone on a bit late. So,
ICTS questions?
Yeah, somebody's coming to the front. No, somebody's leaving.
ICTS, do you have any questions?
We can't hear anything you're saying, but we can see that you're leaving. Yeah.
Okay.
Okay, that's my co-author, Girish.
Okay.
Okay. Yeah.
Tiago?
Yeah.
Modular invariance is like all powerful. I mean, once you have ensured modular invariance, then it appears that you are also able to construct correlation functions which are crossing.
In the case where you ensure both modular invariance and integrality of the coefficients, that's a very key part of the search, which is not there in the meromorphic or one character case. Modular invariance ensures integrality, but you find lots of things that aren't theories. It's very strange.
So are you saying that, okay, modular, so in principle I'm saying that, the modular invariance check and the crossing symmetry check, these are, it should not be subsumed, the crossing symmetry check should not be subsumed in the modular invariance.
Apparently in these examples it seems to be, but it's not clear. Yeah, I mean, for example, in Deligne-Cvitanovic models that is a fact, that this Deligne series we found all satisfy crossing symmetry because anyway they are known theories.
Yes.
So in some sense, if they are already known, they have to satisfy everything. So the question is how much luck was involved in landing on known theories. For that matter, in two-character theories, why did we always land on known theories? That was puzzling.
Sorry, Sunil,
Yeah.
you explained this to us last time. Can you give us just 2 minutes? The key element here is that you know that there's a certain number of characters, you can write down a differential equation and sometimes solve it.
Yes, yes.
Just what is the logic behind that?
Oh, very good. So that I think it's just the Wronskian method. So it's like a standard trick of mathematical physics. So if you have, let's say, f1 up to fn, and if you know that under some transformation, you have f1 up to fn. You just have n functions, and you want a differential equation of which these are the linearly independent solutions. So you make Wronskians w, which have f1 to fn, and then it's one variable, so del f1 up to del fn. Keep going, and you skip one line. So del n, let's say del k minus 1 f1 up to n, then del k plus 1 f1 up to fn, and finally in the last line del n. So this is, as you can see, a square matrix because one line is missing, but there's also a line with no derivative, and the missing line can be moved up or down and gives you different Wronskians. Then the theorem is that del n f plus w, I don't know, 1 del w, no, w, 1, no, w n minus 1. So I think w n del n plus w n minus 1 plus f is equal to 0. And the way you prove it is just using the fact that determinant vanishes if two rows are the same. It's a very simple proof.
So at the moment you don't know what the f's are, you don't know what the Wronskians.
Yeah, but the difference is the f's are holomorphic, but they are not invariant under crossing or modular transformation. They transform as a thing, but the Wronskians are invariant because when any f goes to a linear combination of others, the determinant doesn't care. So the Wronskians are both holomorphic and invariant. This is the key.
Enough to give you a basis.
That's enough to give you the differential equation.
Meaning you know it unambiguously or up to some unknown constants.
So overall constant is always unknown because it's linear homogeneous. As far as you know it unambiguously because now the point is you don't know these Wronskians either, but you know their singular behavior at all coincident points and at infinity, and that determines the function completely because it's holomorphic and single valued under crossing. That's the main point. Being single valued and holomorphic on the complex plane, Riemann's theorem or whatever tells you everything you need to know about it.
And so therefore you can solve for the Wronskian.
Therefore you can solve for all the Wronskians.
And then
solve the difference. That's the idea. Now there is some caveat, which is that you can't guarantee that these f's don't have some spurious zeros in various places. And there's some kind of theorem that doesn't happen for low numbers of blocks. But after 3 or 4 blocks, there may be some spurious zeros, and then you might have not fixed the Wronskian correctly. We assume that the only spurious poles, excuse me. We assume the only poles are when two fields come close.
So as you said probably in your talk, this is an alternate way of solving for all the minimal models?
No. So it'll give you the differential equation for correlation function only for those fields whose fusion rule produces at most 2 fields on the right side, which is certainly not all the minimal models.
Why was that important?
Because second order. If it's higher order, then you have this problem of spurious poles. Secondly, so it's not a replacement for minimal models, it's a replacement for only the low degree minimal models. Although there's an infinite family of minimal models, all of which have a field phi 2, 1. So you can find the 4-point function for all of them. But for characters, you can only do it for the Ising model. You can't even do it for tri-critical because that would be a 6th order differential equation. So I guess I really should go because these people are waiting for me for lunch. Yeah, thank you. Thanks.